Hi, my name is Brit Youngman from Tel Aviv University, and this is a joint work with Shai Gershton and Professor Tova Milo, also from Tel Aviv University. So inference maximization is a well-studied problem whose goal is to find a bounded-side set of influential users in a social network so that their aggregated influence on others is maximized. The motivation of this work is as follows. Consider a government office aimed to spread a message regarding the new vaccination policy. On one hand, a main goal is to reach the largest possible number of users. However, at the same time, it is also desirable to maximize the number of reached anti-vaccination users. Standard influence maximization algorithm will only maximize the overall influence. On the other hand, a targeted IAM algorithm, the one that is focused on a specific subgroup, will influence the influence over this specific particular group. As we show in this work, maximize the influence over one group may come at significantly reduce the influence over another group. Continuing with our own example, maximize the influence over anti-vaccination users may reduce the overall influence. To this end, we present the IAM balance system, which allows users to explicitly declare the desired balance between multiple subpopulations of interest, namely multiple objectives. IAM balance employs a refined notion of the classic IAM problem, which we call the multi-objective influence maximization, where all objectives except one are turned into constraint, and the remaining objective is optimized subject to this constraint. Our contribution can be summarized as follows. We formally define the multi-objective influence maximization problem. We prove the hardness of optimization of this problem, in particular showing it to be harder to approximate than the classical influence maximization problem. And we provide a tight randomized linear programming-based algorithm which solves this problem, and also devise a nearly optimal in terms of running time algorithm, which employs state-of-the-art IAM algorithm as an input. Intuitively, we define our problem as follows. We start by defining the classical influence maximization problem, which defined as the problem define a case-size set of users whose aggregated influence over all users is maximized. The group-oriented influence maximization problem, which often called the targeted IAM problem, is given with the input group of users, which we call Z and G, and find a case-size set of users whose aggregated influence over the G member is maximized. For example, continuing with our example, let's assume that K is equal to G1 are the red nodes and G2 are the blue nodes. The solution that maximizes the G1 cover, namely the influence over the red node, is to select node E and G, where the expected influence is 4. On the other hand, to maximize the influence over the blue node, the optimal solution will be to choose nodes D and F. The multi-objective influence maximization is defined as follows. We start by defining this problem intuitively for only two emphasized groups. However, all of our result and definition holds for the more general case when we have unbounded number of groups. So given two groups, G1 and G2, a threshold parameters T, the goal is to find a case-size set of users whose aggregate influence over the G1 member is maximized, subject to a constraint imposed on the minimal number of G2 member to be influenced, which is defined by the parameter T. Continuing with our example, for T equals 0.1, the optimal solution is S, where the expected influence over the blue node is 0.2, and the expected influence over the red node is 4. Setting T with a higher value, 0.5, S no longer satisfies the constraint, and the solution E and D become the optimal solution where the influence over the red node reduces to 3.25 and the influence over the blue node increases to 1. We generalize the solution space to better the optimization where one may also approximate the constraint. As in the original influence maximization problem, the optimal objective of approximation is 1 minus 1 to the E. We prove that in order to achieve this optimal value, a relaxation of the constraint is necessary. We prove that the multi-objective influence maximization has no as no approximation factor dominate over the generalized bound that was proven for the classical inference maximization problem. As mentioned, we devised two algorithms. Our first, called the RMOIM algorithm, relaxes the constraint and allows its approximation factor, achieving in return the optimization ratio for the objective. However, it solves the problem using linear programming, and therefore its performance becomes polynomial, compared with state-of-the-art inference maximization algorithms, which are linear. We therefore also devised the MOIM algorithm, which runs two single objective targeted IM algorithms and combines their input. It guarantees that the constraint is fully satisfied and not approximated, while providing which come at the cost of a lower approximation value for the objective. However, it achieves near linear time performance as state-of-the-art inference maximization algorithm. We have conducted an experimental study which evaluated the quality results achieved by the algorithm compared with alternative approaches, and also examined the performance of our algorithms in terms of execution time and scalability. The competing algorithm which we examined are standard IM algorithm, target IM algorithm, which focused on particular subgroups of interest, and weighted an inference maximization algorithm where we assigned different weights to user reflecting the relevance to the multiple objective. As I present here, the quality evaluation, we demonstrate the result over multiple group, in this case over 5 emphasized group of users. And as can be seen, only our algorithm, the MOIM algorithm, is the only one that satisfies the constraints for all the first 4 emphasized group. And in most cases, as you can see here in the DBLP dataset, is inference over the objective, which in this case is the G5 group, is the second best. And in the second example, in the POCEC, it's influence over the objective. The G5 again is on the par with other state-of-the-art targeted or weighted IM algorithm. The RMOIM algorithm, our algorithm that relaxes the constraint, as can be seen, does not satisfy the constraint in all cases. However, its influence over the objective is the best among all the competitor, or the second best among all the competitors. Regarding the scalability evaluation, as can be seen, our MOIM algorithm is on the par with state-of-the-art IM algorithm. In this case, we examine the IMM algorithm, which is a state-of-the-art algorithm for the inference maximization problem. And as can be seen, our MOIM algorithm takes significantly longer because, as mentioned, time complexity is polynomial compared with state-of-the-art IM algorithm, which our time complexity are linear. Concluding, we have presented a multi-objective inference maximization problem to handle multiple objectives. We motivated the practical relevance for this problem and proposed two algorithms. Our system, called IM Balance, employs RMOIM for social network, including up to 20 million users and links, and the MOIM algorithm for larger networks, as was proven to be efficient by experimental studies. Thank you very much for listening. Have you have any question?